All right, hello and welcome to Biochemistry 103, continuing with molecules, this time looking at things like functional groups, isomers, and different types of hydrocarbons. We have three objectives today. We are going to construct hydrocarbons and classify them as A, either saturated or unsaturated, and B, as either linear, ringed, or branched hydrocarbons. Number two, we're going to describe the significance of isomers in biology and classify them as either structural or geometric enantiomers or geometric cis-trans pairs. Okay? And our third objective today, we're going to describe the properties of molecules that contain functional groups. In other words, once we know that a molecule contains a functional group, we'll be able to predict some of its properties. Okay? And again, we're going to be revisiting a concept we've had several times: structure, property, and function. So without further ado, let's have a look at objective number one: drawing hydrocarbons as either linear, branched, or ringed molecules. Now, hydrocarbons, as the name would suggest, are molecules that contain at least two types of atoms, that is, carbon and, of course, hydrogen. Okay? And basically, we need to follow three rules when we're drawing hydrocarbons. All hydrocarbons adhere to three rules. The first rule is that any hydrocarbon has a molecular formula, and that molecular formula tells you how many of each of the types of atoms, how many carbons or how many hydrogens. For example, something like C3H6, okay, obviously has 3 carbons and 6 hydrogens. So whenever we're giving a molecular formula, we're always going to look and determine and make sure that we have the right number of each type of atoms. Okay, number two, second rule. Every carbon, we know it has a valency of 4 from the previous lesson on atoms, wants to form 4 shared pair of electron bonds. Okay, it wants to do that. Now it can do that in a number of different ways. It can either do that with a single bond, which we will draw today as a single dashed line, a double bond, okay, which would be, of course, a double line, triple bond, 1, 2, 3, and finally a quadruple bond is possible between two carbons, 1, 2, 3, 4. Now, given that the carbon has a valency of 4, it's going to want to always have 4 shared pairs of electrons. So if a carbon has single bonds, it's going to need to have 4 of those. 4 ones is 4. But if a carbon has double bonds, how many double bonds would it need to have? Well, it wants to have 4 total, so that would be 2 times 2 would be 2 double bonds. You can have a triple bond and a single bond, but of course a carbon can only have 1 quadruple bond. So these are the type of bonds we're always going to draw with carbons. Now, in relation to hydrogen, hydrogen has a valency of 1. So hydrogen is only going to be able to form a bond with 1 shared pair of electrons. So no matter what, we're always going to have single bonds with hydrogens. Okay, these are going to be single bonds. Okay, now how can we predict what kind of bonds will we have in C3H6? In order to achieve objective number 1, we need to be able to draw a molecule like this. Well, let's go ahead and have a go. Now we're going to follow the 3 rules that we laid out. Again, those 3 rules are: we're going to make sure that we have the correct number of carbons, in this case 3, hydrogens, in this case 6. We're going to make sure that every carbon has 4 bonds, 4 shared pairs of electrons, which it can do in the form of either single, double, triple, or quadruple bonds, and every hydrogen has 1. If we follow those rules, then we'll have correctly drawn a hydrocarbon. So let's go ahead and see what C3H6 would look like. Now, we're talking about carbon-based molecules, so we need to make sure we start with carbons, and I've got 3 of those. And I've chosen to draw my 3 in a straight line. And this is what a linear molecule is. It is a molecule with carbons lined up in a straight line like this. Okay, we can call this carbon 1, carbon 2, and carbon 3. Okay, so carbon 1, 2, and 3. Okay, now carbon 1 already has 1 bond, so it needs to have 3 more. Okay, it requires 3 more bonds. As we add the hydrogens, we'll have to figure out how those bonds will appear. Carbon number 2 already has 2 bonds, 1 in the back and 1 in the front, so it can have at most 2 more. And the third carbon over here has only 1 as well. So how will the hydrogens be added to this? Well, to be honest with you, when you're doing these, it's like doing a jigsaw puzzle, okay? You try a piece in a certain place. If it doesn't fit, you move it, you turn it around. So we're going to try some various things. One piece of advice I'll always give you is start with the carbons on the ends. It's a lot easier to add double and triple bonds here between 1 and 2 and between 2 and 3, but obviously if we're adding hydrogens, we know rule number 3, hydrogens can only have single bonds. So let's go ahead and add 3 to this carbon. Okay, why 3? Well, let's just try 3. We could try 2, we could try 1. So I'll do 3 first, and then we'll see what would happen if I added maybe 2. Okay, and we'll figure our way through this. So first of all, let's do that. Here's 1 hydrogen over here. We're going to add a second hydrogen over here and a third over here. And there's our 3 hydrogens. Okay. Now these 3 hydrogens all have single bonds to the carbon, carbon number 1. So that means that it has 3 bonds, 1 with each of these hydrogens, and a single bond to a carbon. So this carbon is already completely full. It can't take any more bonds. Okay, it is completely and totally saturated. You can't add any more atoms in here, so we're not going to. All right. What about this second carbon over here? Well, again, follow the rules. I would really advise you not to start filling in the middle carbons before you fill the ends. It's a little bit easier to manipulate around. So I'm going to skip past carbon number 2, and we're going to go to carbon number 3. Now you might think, oh, could we add 3 hydrogens over here? Well, let's look at what would happen if we did that. And the answer would be no. C3H6 can't form this way. Why not? Because we've broken one of the rules. Look at carbon number 2. It only has single bonds. So I know that this could not be the case. So let's go ahead and remove those hydrogens. I know it can't be 3, so let's go ahead and try another number. Let's try 2. So I'm going to add a hydrogen here and add a hydrogen here. Now if I add 2, this carbon is still not happy. Okay, on top of that, I still don't have enough hydrogen, so I need to add 1 more. If I'm not adding it to the first, because I can't, it's completely saturated. I've already tried 3, and that leaves me with the second, so I'll stick it in there. Now I'm still not okay. All right, although I have the correct number of carbons and the correct number of hydrogens, I haven't obeyed the rules of how many bonds each must have. This first carbon has 4, that's good. But the second carbon has 3, and this third carbon has 3. And I can't add any more atoms. But remember, carbons can have single, double, triple, or quadruple bonds. So just by adding a little bond in here and making this a double bond, we have got everything satisfied. Of course, you need to go back and check. So let's do that real quick. I got 3 carbons. I got 6 hydrogens. I have 4 bonds for every carbon, sharing 4 shared pair of electrons. And every hydrogen has 1. Okay, so this is a correct molecule. Now let's look at this molecule and let's finish off objective number 1. Not only do we need to be able to draw these hydrocarbons, we need to be able to describe them as saturated or unsaturated. Now what that means is a hydrocarbon that is saturated is a hydrocarbon that couldn't take any more atoms. The easiest atom to take, of course, is hydrogen because it only requires 1 shared pair of electrons. So it's probably easiest to say, can we add more hydrogens to this molecule? Well, let's look at this CH36 molecule that we've just drawn. Is it saturated or unsaturated? Could I add more hydrogens? Well, the answer is yes, I could. What I could do is I could take away the double bond that I added, okay, and I could add, potentially, it won't be C3H6 anymore, but I could add 2 more hydrogens, 1 here and 1 here, okay? Now this molecule is not C3H6, this is C3H8. And it is saturated. Why is it saturated? Well, you'll see that every carbon has a single bond and every hydrogen has a single bond, and they all have the required number of bonds. There is no more space for any other atoms. Now, a quick and easy way to see if something is saturated or unsaturated is to simply look at the carbon skeleton. If there are all single bonds between the carbons, it is a saturated molecule. If there are double, triple, or even the possibility of a quadruple bond between carbons, then it is unsaturated. So it's pretty easy to be able to see that. Now, why do we use this word saturated? Well, what saturated means in biology or in general language is when you have something that can't take any more. If you go outside and stand in the rain and you get wet, you start thinking to yourself, well, I better get home before I get too wet. But there reaches a point where you're absolutely soaked through, where you simply can't get any more wet. You are described as saturated, where it's like, what difference does it make? I'm completely saturated. I may as well not worry about it. Okay, so same thing here with these hydrocarbons. When they have completely taken on as many bonds as they can, that would be every carbon has single bonds, they are saturated. If not, they are unsaturated. But we can also classify this molecule another way. I drew the carbons originally in my C3H6 molecules. Let's go back to that molecule for a moment. Here's my C3H6 molecule. And I drew this molecule as a linear molecule. Why is this linear? Well, you will see the carbons are in a line. Okay, it's one carbon connected to the next in a line. Okay, whether that line is straight or whether it's bent or kinked, it doesn't matter. It's a linear molecule. But we can draw another type of C3H6. So let's go ahead and do that. And this time we're going to draw the molecule C3H6 as a ringed molecule. Okay? So, what's the difference? Well, the first thing we do always is to draw our carbon skeleton. Let's do that. And in a ringed molecule, what that means is that the 3 carbons are connected in as close to what we can get to a ring. They're connected in a sort of a circle. In this case, of course, it's a triangle. If we had 4 of them, it would be more of a square shape, but you get the idea that it goes around in a ring. Each carbon is now connected to 2 other carbons. Okay, there are no end carbons. Okay, so this is a ringed molecule. Now, here we got the C3s, and next thing we're going to do is add our hydrogens. In the linear molecules, I told you to add the hydrogens at the ends first because it's easier. There is no end, so we'll just go ahead and add hydrogens. The most I can add to any carbon is 2, and I have 3 hydrogens, so that works out perfectly, and I can draw my C3H6. Okay, now here is C3H6 in a different molecule. Okay, although it contains the same atoms, it actually is a different structure. Okay, this is an example of what we'll talk about in objective number 2 when we talk about isomers. But for the moment, let's just concentrate on objective number 1. Here is C3H6 again in ringed form. Why is it ringed? Because the carbons form a ring. Okay, has to be the carbons. Is it saturated or unsaturated? Well, you'll clearly see that every bond is a single bond. Every carbon has the maximum quotient of bonds, and so does every hydrogen. So this is a saturated, ringed C3H6 molecule. Okay? All right, so let's draw some more hydrocarbons. And let's throw in some other atoms as well. So for now, what I like to do is draw a molecule, and this molecule is going to have something we'll call a functional group. Okay, I'm going to jump too far ahead. Okay, but I'm also going to draw what's called a branched molecule. So for objective number 1, we talked about linear molecules and ringed molecules. Okay, now you can't draw C3H6 as a branched molecule, and the reason that you can't draw C3H6 as a branched molecule is once you put the 3 carbons in a ring, there isn't another carbon to add as a branch. A branched molecule requires more carbons than that. Okay, in fact, the minimum number of carbons that a branched molecule can have would be 4, right? You could put 3 in a line and 1. We're going to draw a backbone of 4 carbons, and we're going to draw a branch coming off over here. Okay, and this branch could be 1 carbon long, or it could be 2. You could have another branch over here, so let's go ahead and do that. Okay, and all of these things are possible. This is how we can build up these big skeletons. Okay, now if this was a saturated molecule, well, let's look at how many hydrogens would be required for this molecule. So looking at this first carbon over here at the left hand side, we'll see that it has a single bond, so we would have to have 3 hydrogens there to satisfy that carbon. Okay, how about this second one over here? Well, it already has 3 single bonds to other carbons, so we'd have to add another hydrogen up here, and it's satisfied. This carbon over here has 3 bonds to other carbons, so again it requires only 1 hydrogen. And let's finish off our chain first, and that leaves us the carbon at the end over here. We'd have to add 3 hydrogens to this one in order to make all the rules satisfied. Okay, how about this carbon over here, our branch carbon, or these 2 carbons down here? Well, they just obey the same rules exactly, so we would have to add 3 hydrogens here, 1, 2, and 3. And of course we'd have to do something similar down here. Not 3 because this carbon down here has 2, so we have to add 2 more. That's 2 more H's here. And we'd have to add 3 to this final molecule over here on the final carbon.